Okay. Okay. Now. All right. So let's get started. So as you can see, today our topic is deep transfer learning and multitask learning. These are two of the most fundamental topics in deep learning, which have proven to be very useful. So let's begin with transfer learning. So what does transfer learning mean? Well, it literally means transferring model that is trained on source data A to target data B. Specifically, there are two types of transfer. Of course, these can mix and match, but basically you can have two types of transfer. First is task transfer. So task transfer means you adapt one task, a model that is trained for one task, to another task. Now, in this case, the source and target data can be the same because you can perform different tasks on these two different tasks and on the same data. For example, if you have an image classification task, maybe you can adapt the model to make it do image segmentation. That is, tell you how many segments, how many types of semantics there is within the image. Also, if you have a task for machine translation, based on your text, then you can maybe do sentiment analysis, like what kind of sentiment, what kind of thoughts is this text exhibiting. And also next, we have maybe time series prediction, using existing observations in the time series to predict new observations, future observations within the time series. And you can adapt to the model to time series classification. That is, for example, I give you a time series and you tell me what the label is, what label that is attached to it, and etc. The other type of transfer is data transfer. In this case, we transfer a model that is trained upon one batch of data and adapted to a different but related type of data. In here, the source and target data are definitely different. For example, if you have trained a model on images of everyday objects, and now you can use transfer learning to transfer it to medical images. Also, if you have a text mining model for Chinese, and maybe you can adapt it to English. Also, in biomedicine, maybe you have physiological signals for one patient, you have the monitoring algorithm for this patient, and you can transfer it to another patient. So the rationale behind transfer learning is that what makes transferring possible is because similar features can be useful in different tasks. For example, the similar features for one time series can be both used for prediction and classification. And all these features can be shared by different yet related data. Everyday objects and medical images are both images, so there are some semantic similarities between them. Now, so let's take a look at the taxonomy of transfer learning. Depending on whether the source data and the target data is labeled, we have these four broad types of transfer learning. So if they are both labeled, the first type of transfer learning, which is transfer learning, if you define it narrowly, transfer learning means model fine-tuning. That is, you have a model, and when you are trying to adapt it to new data or new task, we need to fine-tune its parameters to make the adaptation happen. So that is a model fine-tuning. The other is another topic for today, which is multitask learning. But usually we do not call multitask learning. We tend to talk about it individually rather than part of transfer learning. But anyway, we will be talking about this later today. And also, if you have source data that is unlabeled, but the target data is labeled, then the first type of thing is what you can do is called domain adversarial learning, and the other is zero-shot learning. And these two are very interesting topics, and which deserve their own seminars. So I'm not going to touch these today. And also, if you have target data that is unlabeled, then you have self-taught learning and self-taught clustering. And these two, they do not see as much application as the others. So we're not going to touch them today. So basically, we're going to focus today on the first type, that is both like the source and target is both labeled. So we will begin with model fine-tuning, which is narrowly what we mean by transfer learning. Okay, so what is model fine-tuning? So if you have a trained model on a large amount of labeled source data, and you want to transfer it to a target data set with very little labeled target data, for example, if you want to do medical image segmentation, you may have segmentations of many images of daily scenes, but you only have several medical images that have already been segmented. So in this case, you can transfer the daily data to medical data. For speech recognition, you may have audio data and transcripts of many historical speakers, but you only have limited audio data and transcripts for a new speaker. Like when you are using any kind of such as Cortana or Siri, you don't typically need to speak a lot to train it. Because they have a lot of historical data embedded in them, and they will use transfer learning to adapt to your new voice. And also for arrhythmia detection, that is a heart condition, you may have very long ECG signals for a large number of historical patients. But for a new patient, maybe you're just gonna take a 10-second snippet of his personal data, and we are going to use this snippet to adapt the previous model. So the idea is we pre-train a model using the historical source data, and then we will fine-tune the data with the target labeled target data. Here, an important concern is because the amount of target data is really scarce, if you pay too much attention on it, you're likely going to overfit your model, and the model does not really generalize well. So you will see that it performs very well on the target training set, the already labeled data itself, but for future data, it's going to perform poorly. So we do not want overfitting to happen. This is an important issue we are going to need to deal with when we are defining our transfer learning model. So how does it work? The first basic type of transfer learning is called conservative training. So for example, here from the left, we have a pre-trained model on the source data set. Of course, deep learning models, you have input layer, output layer, and what really matters is the hidden layers. Okay, so how do we make the transfer? So on the other side, we have an identical network that is in terms of architecture. And we are going to, use these parameters of the pre-trained model, the parameters of the hidden layers, to initialize the parameters of this new model. And then we are going to use the target data to, further train this model, to further fine-tune all these parameters that is directly copied from the pre-trained model. Now you need to limit the number of epochs of training. For example, if you have trained on your historic data for maybe 100 epochs, here maybe you just train 10 epochs, something like that, to limit the number so that you do not overfit your very scarce new data. Okay, so based on this idea of conservative training, we can go one step further to layer transfer. Here we know that we have several hidden layers in these. Let's say, for example, the pre-trained model has 3 hidden layers, and of course the new model will also have 3 hidden layers because we are copying the architecture. Again, we will initialize the parameters, all 3 of these layers using the previous parameter set in the pre-trained model. But instead of fine-tuning all these parameters, we can freeze the parameters of some hidden layers. For example, let's say for the hidden layer 1 and hidden layer 2, we're going to freeze them. That is, these weights, these model parameters will not be changed, and we will only fine-tune the parameters of the other layers on the target data. That is, we're going to tune hidden layer 3. And also in this case, we want to limit the number of epochs to avoid overfitting. And this freezing itself can also, avoid overfitting, because if you don't freeze this, then you will have a large number of parameters to tune, and generally speaking, it's not very ideal if you have a lot of parameters to tune, but you only have very limited data. And in this case, after freezing these two layers, if we only have layer 3, and then we will have much fewer parameters, and this will match better with the limited data we have and avoid overfitting. So generally speaking, you can freeze either the first or the last few layers, which we will show in the hands-on experiments later. Okay, so one of the most important, one of the most valuable things I think for non-IT users, that is people not have much expertise in computer science, is how do you choose the pre-trained models? Now, there are a lot of open source pre-trained models for transfer learning, and it is generally advisable that you use these open source pre-trained models as the base model for your transfer learning. For example, for natural language processing, we have BERT, we have GPT-3, and for computer vision, we have VGG16, we have ResNet50, we have VIT, and let's go through these one by one, see what they are like and where you can get them, so that you can directly plug them into your own applications. Okay, so BERT. First, BERT. What does BERT stand for? BERT stands for bidirectional encoder representations from transformers. And this is a natural language processing model that was proposed by Google in 2018, which immediately gained a lot of attention because it was performing really well. So it was pre-trained on 2,500 million words from Wikipedia and 800 million words of the book corpus. So it is trained on a large number of text data, and this kind of a large-scale training is not applicable for us, for people like us. We do not have the computational resources as Google does. So it is really good that we can directly download this model and plug it in, so that we can use all this knowledge embedded in these large corpuses. And it allows for training customized question answering models in just a few hours using a single GPU. So if you have the base model ready, and you can just go continue optimizing it or continue fine-tuning it, and you can just get your own customized model very soon. And you can download this model here, the source code. And there are quite a few variants like CodeBERT, Robert A, and Albert, XL and XLNet, stuff like this. They are all variants of BERT, which are, to the best of my knowledge, are all open source, so you can directly use them in your own NLP applications. The other one we are going to talk about is GPT-3. The full name is Generative Pre-trained Transformer 3, and it's also for natural language processing. It was proposed by OpenAI in 2020, and again, it's trained on this huge corpus. It has a huge number of parameters. It has 175 billion parameters, and the number of parameters within this model is really staggering, because it is 10 times more than any previous non-sparse language models. And it is really strong at tasks such as translation, answering questions, and some stuff like answering like on-the-fly reasoning-based tasks like unscrambling words. That is, if you scramble the words within a sentence, you want to recover the sentence, it does really well on this. And also, it has seen a lot of real-world applications like writing news and even generating codes for programmers. And it is a bit of a controversial model, I would say, because it is too powerful. So even people over at OpenAI, when they publish this paper, they say, you guys need to do something about this. Otherwise, it will definitely be misused. But anyway, it is a very powerful tool, and they have an API for this if you want to try it out. All right, so moving on from NLP, we are going to take a look at some computer vision models. The first one is VGG16. So VGG16 is a computer vision model that was proposed by the Visual Geometry Group from Oxford, hence the abbreviation VGG. And it was pre-trained on an ImageNet corpus, which basically all the open source computer vision models are trained on ImageNet. And it is the first runner-up of this competition in the classification task, so it did really well. And it is a CNN model. I believe that previously in Fula's tutorials, she told you about how CNNs are ideally suitable for computer vision tasks. And why the 16 here means that it has 16 layers and it has about 138 million parameters. And this model is so classic that it has been built into popular deep learning frameworks such as PyTorch and Keras. So you can just basically import these models with a few lines of code. And it's got a variant, a relatively popular variant called VGG19, which means it has 19 layers. I'm not going to expand on here. So this model is somewhat classic. It was proposed in 2014, which for deep learning is really a long time ago, but still it is pretty popular today. And after VGG16, another very popular, very widely used computer vision model is called ResNet-50. So it is a variant of the ResNet model. And again, it is pre-trained on ImageNet. It was proposed by, the ResNet model was proposed by Microsoft in 2015. And again, the 50 means that there are 50 layers within the model, and it's also CNN. It has about 380 million parameters. Again, it is very popular, so you can just basically call them in popular deep learning frameworks. And finally, we're going to have something really fashionable that is really new, but basically has seen huge success in the past 1 year or two, which is called VIT, or Vision Transformer. If you can recall, I have basically the two open source NLP models we just discovered, we all have the word transformer in them, because transformer is a very, 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 very popular, very, very strong model for processing text data. But in this one, which was proposed in 2020 by Google, they actually introduces the transformer architecture from NLP to computer vision. The idea is basically treating patches in images as words in text. And when this transformation was done, this model achieved huge success because it achieved better accuracy and efficiency. That it is better, it's more accurate but faster than CNNs such as ResNet-50. So this is at the forefront of today's computer vision research, and I highly recommend you can really think about using this model within your applications, especially when you are dealing with computer vision. It can be obtained here, and also it's got quite some variants like swing transformer or PVT v2, etc. So this is a very new but very powerful pre-trained model that you can try out. Okay, so we are halfway through today's seminar, and we are going to pause here and take a look at the hands-on experiments for model fine-tuning. Before we move on, any questions so far? Okay, if we don't have any questions, let's take a look at this seminar. Okay, transfer learning. Okay, so here we are going to do transfer learning using VGG16. We have just mentioned it. It's a very classic computer vision model. We are going to do image classification. So okay, let's first look at what the data set is like. Okay, it's gonna take just a while to load the data set. It's not going to be take very long time. Okay, we have loaded the data set here. As you can see, we have X-trained, like the shape is like this. And so we have 50,000 images for training and 10,000 images for testing. Each of these images is 32 by 32. The 3 means that we have RGB images which has 3 colors, 3 color channels. So so this is basically our data set. Now let's see what happens if we load the data. Let's load the pre-trained VGG model, and here we are using Keras, which is a very popular deep learning network. And as you can see, we basically just took one line of code to load this VGG16 model. So it's very, very ready to use, very off the shelf. And as I mentioned, for layer transfer, we need to freeze the layers. And in this case, we are going to first freeze all the layers of VGG16. So as you can see, we are setting every single layer to be not trainable. Here we have a list of all the layers within VGG16. As you can see, the false indicates that they are all freezed. Okay, so the VGG16 is a general feature extractor. And now we need to add some layers on top of VGG16 to actually do the image classification. So that's what we're going to do now. And yeah, okay. So as you can see, we have the base VGG16 model, which is frozen. And then we have added some dense layers and some dropout layers. The details are not really important. All these new layers are used for doing the classification. So we have these. Let's see. We have something like more than 500,000 trainable parameters that have not been frozen, as opposed to all the parameters in VGG16 that have been frozen. All right. So we're now going to train this network and see how well it performs. Okay. The actual training will take a while, but I have just loaded a pre-trained model. So as you can see, let's focus on this accuracy, especially on the validation set. So after like 8 or 9 epochs, we got something like 0.6 accuracy, which is somewhat decent. But let's see if we can do better. So the idea is, you remember we had the VGG16 model all freezed. Now let's unfreeze two blocks within it, like this, something like something like this, and we're going to fine tune these 2 blocks in VGG16 using the same data, and let's see what happens if we further fine tune them. Okay, so again, I've loaded a pre-trained model because this is going to take a while in real time. And as you can see, well, to begin with, as soon as we start actually doing the retrain, we have the classification accuracy immediately boosted from 0.6 to something like 0.66, and eventually it reaches a point which is basically 0.7. So it's a 10 point jump, which is pretty a huge leap. But here, as you can see, for the previous model, the pre-trained model, we trained it for 9 epochs. But here for the new for the transferred model, we only trained for 3 epochs. And that's how amazing these 3 epochs can do. So transfer learning can really help boost the performance of your models. Okay, so this is for the transfer learning part. Any questions? Okay, so if we have no more questions, let's go into the second part, which is multitask learning. Okay, so what does multitask learning mean? It means simultaneously undertaking multiple tasks using a single neural network. For example, for ECG heartbeat to monitor a person's heart, you can use a long-term ECG signal which is periodic. And what you want to do in many cases is that you want to segment these heartbeats into individual ones and label each individual heartbeat with whether it is normal or not. So what we can do is we can use a single network to simultaneously do the segmentation and the classification of these heartbeats. And also, this is a project that I'm working right now at diiP. So we are interested in neutrino event reconstruction. Here we have two prediction tasks. First is for a neutrino, which is a type of particle. We want to know how much energy it carries, and also we want to know which direction it came in from. And for these two separate tasks, we can actually do them under a single network. So there are many cases where you have a lot of tasks that are related to each other, so you can just bundle them up under the MTL framework. But in many cases, we don't necessarily need multiple main tasks. Rather, we can have one main task and several auxiliary tasks to support the main task, which all these, the main task and all these auxiliary tasks can be bundled up under the same one single MTL network. And for example, we have something like called domain adaptation, something called self-supervision. These both of these auxiliary tasks are really interesting. So we are going to do them in separate seminars in the future. Domain adaptation, I believe, is going to be the next seminar, and self-supervision, if we have time, we are definitely going to do this. So we're not going to expand on them today. So back to MTL itself, the two basic forms of MTL is called hard parameter sharing and soft parameter sharing. Okay, so what does hard parameter sharing mean? Okay, let's take a look at this neural network on the right side. So we have one input layer for both tasks A and B. Here we are assuming that tasks A and B share the same data, but in reality, they don't have to. And for the output, we have the outputs for task A and task B. And what you see here is before these task-specific layers for each of these tasks, we have a shared layer. We have some shared layers. These shared layers, the parameter of these layers are identical for task A and task B, which is why we call it hard parameter sharing, because it has to be identical. And these shared parts usually function as feature extractor. For example, you recall that the previous hands-on exercise we did just now with transfer learning, you had VG16 as the feature extractor that extracts all the features from the images. And then you have some dense layers to actually do the image classification. Same thing applies here. Because as I mentioned, the same features can be applied to different tasks. So here the idea is we are going to use the common features extracted from the data and just feed them into different downstream tasks to obtain the final results. All right. So this is, okay, sorry. There was something wrong with the ordering of the PowerPoint. So next, take a look at soft parameter sharing. What does soft parameter sharing mean? Okay, let's take a look again at this particular network. For example, if we just ignore this red arrow in between these two, you can treat them as two different networks. For example, you have task A, you have these individual layers. For example, you have these individual hidden layers, and it has its own set of parameters. Also for task B, the same story applies. But here we have some layers called constrained layers. And what does constrained layer mean? It means that although theoretically they have different parameters, we use some measure to make sure that their parameters are same, not the same, no, not the same, almost the same or similar, or they're kind of related. And the similarity or relatedness of these parameters can be controlled by either a regularization term in loss function. For example, we can have a loss function measuring the distance between a set of parameters for task A and for task B. Or we can, add some connections between the constrained layers. So for example, we can have some connections going from task A's constrained layers to task B's constrained layers, so that they can share information, and to make sure that the entire network is intertwined with each other. Okay, so these are two types of basic forms of multitask learning. So why does multitask learning work? There are many reasons, but we are only going to list two here. The first is implicit data augmentation. So data augmentation basically means you get more data to train your model so that it fits your task better. Okay, let's say if we have different tasks and they have different input data, then each task can benefit from the extra knowledge encoded in the input of the other tasks. So this is literally more data. But what if we have all the tasks sharing the same data? Well, the volume of data is not augmented, but we can simultaneously learn multiple tasks to reduce the risk of overfitting for each one of these tasks. Because they are all intertwined, we want all of them to perform better. And if you are using a single task learning for one task, maybe you are performing really well on the task, but it will the parameters, the features that is learned that is supposed to work for other tasks may not work. So in this case, sharing all these tasks within one MTL framework can actually mitigate this problem. The other reason is that we can do enhanced feature learning. All right, just to pick up where we left off just now. In a specific task can be very noisy, so that we may not be able to learn the most relevant features if we only deal with a particular task. But including other tasks makes it easier to uncover truly relevant features. Also, for some features, it is easier to learn for some tasks than the others. Sometimes maybe the features are not that hard to learn by themselves, but the task is really not fitted to uncover these features. So this can be done by using other tasks to make it easier to enhance the performance of these specific tasks that it's hard, on which the features are hard to be uncovered. Okay, so this is the basic theory about MTL. Any questions so far? Okay, then now let's move into some specific examples on MTL. And the first example is image segmentation and depth regression. So let me first explain what these terms mean. For example, you have an input image here. This network is trying to do three tasks. The first one is called semantic segmentation. That is, we want to segment this input image into different areas, in which each area has its coherent and independent semantics. For example, there are people, and here's a bicycle, and there are some lamps, and they are all segmented from each other. The second task is called instance segmentation. That is, we are going to, based on the semantic segmentation, we are going to omit all the background information. We're just going to pick out the most important instances, the most important objects within the image. For example, people and the bicycle. And the third is called depth regression. That is, we want to know how far away each of these pixels is from the camera. That's called depth regression. And here we have a hard parameter sharing MTL network for these three tasks. We have a shared encoder that is a shared feature learner. For example, it can be VGG16 or something else. And then we have the individual downstream task encoders to accomplish all these three tasks. So this is a typical hard parameter sharing example. All right, so the other next example is high definition radar on your cars. And what they do is basically two things. The first thing is called vehicle detection. This is easy, right? So you have these radars on your cars, and you want to know where the other vehicles are. And the other one is free space segmentation, which means the radar wants to find safe spaces for you to drive through. So these two tasks can also be done simultaneously in this one network using hard parameter sharing. So again, we have the input. We have a series of three encoders which are hard parameter shared. They are shared by both of these downstream tasks. And we have two heads. The first head is free space segmentation, and the next head is vehicle detection. And I'm not going to go through the details here, but this is generally how these encoders are being shared. And also for natural language processing, we can have cross-language knowledge transfer. For example, here we have a lot of languages, like maybe you have Chinese, you have Spanish, you have French, you have English, and we want to use one single network to train a model that can be applied to any of these languages. So what do we do? So we have a shared feature extractor, which has many hidden layers, and we are going to input all these training examples or testing examples of different languages into this network. And then we are going to have downstream tasks for each of these individual languages. So again, this is a example of hard parameter sharing. So as you can see, hard parameter sharing, while it is very basic, very simple, it is actually very, very useful. All these examples I've shown you are all published in very reputable journals or conferences. So hard parameter sharing is actually very, very useful. But now let's turn to something a little bit more complex. We're going to have a text classification example. Here we have two individual tasks for text classification. And the authors of this paper actually proposed 3 types of MTL architectures for this task. So if you remember what Fuller told you about in her seminars, text data is kind of a sequential data, and a very effective way of processing sequential data is with RNNs. In this particular case, this is RSTM. So the RSTM has a lot of units, different units. So here, the most fundamental type of MTL for text classification using RSTM is that we have input data, input sequences for the 2 tasks sharing a single RSTM sequence. And eventually we'll have this softmax for the eventual classification. And the next one is a little bit more complicated. It's a soft parameter sharing one. So as you can see, these 2 tasks have their own RSTM sequences, but each RSTM unit within each for each step of each task, they will be connected to the next step of the other task. So this is a kind of constrained layers with connections to each other. And the third is actually a hybrid of soft and hard and soft parameter sharing. So again, we have these individual RSTMs that is directly processing the input, but they are connected by a shared bidirectional RSTM. And so this is a kind of hard parameter sharing, but this hard parameter shared layer is connecting these 2 constrained layers. So this is actually a mix of hard and soft parameter sharing. Okay, so next we have an example on correlated time series forecasting. So what does correlated time series mean? It means that we can see here we have X1, X2, X3. There are 3 time series, and these 3 have some kind of semantic relationship. For example, they may be different sensors within the same sensor network, or different leads for the ECG signals that is for the same person. So naturally they have some connections with each other. And so how is this connection depicted? It can be depicted by MTL. So here we have these individual time series. We are going to first pre-process them with their own feature extractors, but then we are going to use hard parameter sharing. We are going to use a unified forecasting layer to actually do the final job for the forecasting. So this is a little bit different from what we saw before. Before we have this hard parameter sharing at the beginning of this network, but here we have hard parameter sharing at the end. That is the the downstream task is actually done with one single RNN that is a uniform shared network. Okay, so this is for the tutorial today, and here are some references. Any questions so far? Okay, if not, we are going to take a look at the hands-on exercises for multitask learning. Okay, so we have this hands-on exercise for multitask learning, and it's for standard deviation prediction on synthetic data points. Okay, let's first take a look at the synthetic data. What does it look like? Okay, it looks like this. So basically, it's a 2D data. It has X and Y, and it is spread within this 2D space. And the two tasks is to separately predict the standard deviation of these two groups of data. Okay, let's define our MTL model to see how it works. Let's first focus a little bit on the. Okay, let me run this first actually. So we go back here. So how do we define this prediction model? As you can see here, the input, we have some inputs from both these groups, and we are going to use this dense layer with a ReLU activation as the hard parameter shared layer. And then we have these two separate dense layers to actually do the prediction task. So this is basically how the network looks like, and you can see here much easier. The first dense layer is for the parameter sharing. It's a basic feature extractor, and the second and third dense layers actually finishes the downstream task. Okay, so in this case, let's actually train this model to see how it works. Okay, so here we have the results, and the ground truth is for the first group we have 10. And 1, and the predicted for the first one is something like 8.6, and the second is something like 0.9, which it's pretty close. So this is actually how it can be done under the MTL framework. And I'd like to note one thing before we wrap up, is that we haven't talked about how we define the loss function for the MTL, because we have multiple tasks. If you have a single task, you can just define your loss function for that single task. But for MTL, the basic form is something like this. Okay, you have these different tasks. You can just add these add the loss functions for these individual tasks up to obtain the final loss function. Okay, so so we can actually do this, but in reality, you may want to weight them a little bit to obtain the optimal performance. And there are some researches on this, but I'm not going to expand on this. Basically, this is empirically trial and error. So there is something more delicate to this that we need to be aware of when we are using MTL. Okay, so this is for today's seminar. Again, any questions? Okay, I'm seeing this question. Do you have an example on correlated time series? Okay. For correlated time series, the basic thing that you can think of is multi-dimensional time series, or multivariate time series. For example, if we in medicine, as I just mentioned before, we have ECG recordings, and if you have taken an ECG, you will know that the nurses will put a lot of sensors. There's a lot of leads on you, and each of these leads actually can generate its own time series. But as these leads are all depicting your heart condition, all of them are correlated. So this is a type of a correlated time series. Let's maybe take a look. I think we can find some example for this. Hang on, let's see if I can find any pictures of this data set. Yeah, something like this. Okay. So for example, these are two leads that are depicting your body, and they are placed at different positions of your body, but they are both recording what is going on with your heart. So these two are naturally correlated, something like this. Okay, any other questions? Okay. I don't have any hands-on workshops for this, but I do have some data. And if you like, I can actually share with you the data that I have, or at least how to download it, if you wish to get your hands dirty on this. Okay. Okay. So I'm going to talk to Eva later, and I'm going to upload some of the data, or how do you download them, and you can go to our website to check it out. Okay, you're welcome. Okay, any other questions? Okay, so if there are no further questions, this will be today's tutorial. Thank you very much, and we'll see you next time.